So thanks everybody for joining today. This is the first international multi-institutional seminar series. And just to give you some background for those of you who weren't part of some discussions we had a series of discussions really in the height of the pandemic, a bunch of us across coasts, to have just sort of these stimulating conversations on the AGN science that could be enabled by very high spatial resolution observations. And it was motivated by the ORCAS mission. For some of you who haven't heard of it, it's a NASA concept study to enable adaptive optics assisted with a laser beacon that can enable unprecedented spatial resolution from the ground on Keck that can approach 10 milliarc seconds in the optical from the ground. And so during these discussions, we were having a lot of fun, and we thought that it would be really nice to have this sort of focused seminar series, just with AGN experts, where we could just sort of have fun talking about cutting edge science, and specifically on AGNs and in particular nearby AGNs. And we thought it would be a good opportunity to brainstorm, maybe forge some collaborations, and just sort of keep our students stimulated and exposed to cutting edge researchers in the field over the summer. So thanks everybody for joining. If this is your 3,000th hour on Zoom, I really appreciate it. And I should say that this is meant to be sort of informal, where we're really having fun talking about AGN science that you can do and will be able to do with upcoming facilities. So what we were thinking is that we were going to have a format where 40 minutes would be the talk and we wouldn't interrupt it. And then 20 minutes, we would have a general discussion. And Gabby Canaliso and I, so she's the co-organizer, she's here with us, invited a bunch of speakers just to get this thing started in the summer. And we would be happy to continue it for longer than that, depending on interest. So today it is my pleasure to introduce Taro Shimizu. Taro got his PhD from University of Maryland in 2016, working with Rich Mushatsky. And there he worked on the star-forming properties of the Swift bad hard X-ray selected sample of AGNs. And he then moved on to the IRAS submillimeter group at MPE in 2016. And there he is leading the study of the circumnuclear environments of AGNs. He's also the lead scientist developing the code to fit the kinematics close to the AGN. And Taro really has, an impressive background in multi-wavelength astronomy, ranging from hard X-rays to near-infrared and far-infrared with Herschel. And his research really cuts to the heart of some very simple on AGNs and how they impact their circumnuclear environment and star formation in the host galaxies. So Taro is the recipient of the Andrew Wilson Prize for Excellence in Research at UMD. And now he's doing some really cutting edge work using VLT gravity to really give us an unprecedented view of the central, most compact regions around nearby AGNs. So I'm delighted, Taro, that you're here with us today. So I will turn it over to you.
Share my screen. Okay, everything good? Can see my slides?
Yeah, looks great.
Okay, great. Okay, well, thank you very much for the very nice introduction, as well as for the invitation to give this seminar today, this evening for me. As Shobita said, I'm Taro. I'm a postdoc at MPE, and for the last at least year and a half, I've been working with the gravity collaboration to analyze the AGN data we've been getting with VLTI gravity, and really looking at the sub-parsec structure of AGN in the near infrared and what we can do with interferometry. Okay, so I'm here on behalf of the Gravity Collaboration, which is a very large collaboration spanning multiple institutes. So this is everyone that was part of it back in probably 2016, probably when First Light was. So you can see that I'm not even on here anymore, and so the collaboration has been changing a lot. But it really is a huge effort of a lot of people that went into this instrument, and then also into the science that is coming out. And so, as I said, I've been studying AGN with gravity. So since this is a AGN seminar, I don't think I need to convince you that AGN are really interesting to study. But let's go into reasons why we want to use interferometry. As most of you know, I'm sure that AGN structure and the AGN phenomenon expands over a very large range of scales. So this is a nice cartoon from Cristina Ramos Almeida and Claudio Ricci's review article back in 2017. And I like to use it because it shows everything and also gives me nice numbers for the scales. So, of course, AGN, one of the first ways we saw them is through ionization cones, as well as the bright central point source. But the narrow line region and the ionization cones, they're spanning somewhere between 10 parsecs all the way up to kiloparsec scales. And observationally, that's not difficult with single-dish telescopes these days. So just highlighting a couple papers. So Francisco Sanchez, who I think is giving a talk in several weeks, my own paper from a couple of years ago, just showing the ionization cone and the narrow line region. So you can do this with IFU, you can do this with narrowband imaging, and that's not difficult. Now, if you want to get down to the very central regions where the AGN should have the most effect, so something like less than a parsec, where you expect the inner regions of the sort of torus that's emitting in the near infrared and mid infrared, the broadline region, the X-ray corona, and then of course the accretion disk and the supermassive black hole. Now, X-rays and the accretion disk are extremely hard, even with interferometry. Of course, there's EHT, which is giving us the first images of very near what should be the accretion disk of the most massive supermassive black holes. X-rays, I think, are going to be, for an extremely long time, we're not going to be able to spatially resolve them. But with near infrared interferometry, we can start to spatially resolve both the broadline region as well as the inner hot dust structure. And with mid-infrared interferometry, we've already been able to spatially resolve sort of the outer torus structure. So just as a reminder, broadline region should exist something between 0.01 and 0.1 parsecs, and on sky, that's only 0.1 milliarc seconds. Now going out a little farther, the inner region of the torus, hot dust, you get out to milliarc second, several milliarc second scales, 0.1 to 1 parsec. So a couple of questions we want to ask and answer with gravity. Number one, just what is the torus? So previously I showed it's just sort of a bunch of clumpy structure. Of course, we all know, the sort of classical picture of this giant donut, smooth donut, that is causing the obscuration towards AGN and giving us the various zoo of AGN, in particular type 1 versus type 2. Now, mid-infrared interferometry has already sort of begun to chip away at this picture. In in particular, these works by Conrad Tristram, Lopez Gonzaga, and Sebastian Honig have been leaders in this. And so let's just take a look down in the bottom left. This gray line is the equatorial axis that we know from other indicators. And instead, the mid-infrared size is extending perpendicular to that. And so that's sort of already sort of pushed on this classical picture of the torus. And now sort of what's beginning to emerge is that instead we probably have something like a disk structure. So that's also given here in, I think this is Sorcinus galaxy. But a lot of the flux in the mid-infrared is extending into the polar region. And likely, or what's thought is that this is tracing a dusty outflow. So that's mid-infrared, and that's been available for several years. Now the question is, what about the near-infrared? Well, near-infrared should be tracing very hot dust right around the sublimation region. And indeed, early near-infrared interferometers, as well as dust sublimation or dust reverberation mapping, have shown that the sizes that you see from interferometry and reverberation mapping do scale with what you would expect for the sublimation region, i.e. that as a function of the AGN luminosity shown here on the x-axis, the size of the hot dust should go as L to the, or square root of L. But some outstanding questions, of course, is, does this deviate from this relation, and if so, why? And then, of course, besides just measuring sizes, we want to actually image, what does the hot dust structure actually look like? Now, so that's the hot dust. Now, another question is, what is the broadline region? So we know that AGN, type 1 AGN show these very broad emission lines, but what kind of structure are they tracing? So sort of here, Thaisa was fitting broad, double peak broadline regions with sort of an asymmetric dust or a disk structure. But also there's thoughts that the broad emission lines, since they're tracing very high velocity gas, could have a significant outflow component. And so up until now, before gravity, the best way to study broadline regions was through reverberation mapping. And so I'm sure a lot of you know what reverberation mapping is, but in case there's younger students, I want to go through some of the basics so everyone's on the same page. Now, suppose you have a bunch of clouds around the central accretion disk. The accretion disk goes through a sort of change, in this case, maybe a peak. We see that peak at a certain time. The broadline region, or the broadline region clouds, or any kind of clouds around the central continuum structure, also see this change and reverberate or change their emission as a response to that. And then the clouds then re-emit back towards us. Now, because this takes some time for the continuum change to be seen by the surrounding clouds, we then don't see the change in either the dust or the broadline region emission until some time later. And so this results in a time lag. And so based on these time lags, then you can measure how far away these clouds are, just using sort of cross correlation function. And so from these time lags, if you assume that the broadline region clouds are purely under the gravitational influence of the supermassive black hole and are in virial equilibrium, then you should be able to measure the supermassive black hole mass. Now, based on the specific geometry and inclination, there has to be some sort of fudge factor. And so this C tau, which is your time lag times the speed of light, times the dispersion of your emission line over the gravitational constant. That's your virial product shown here on the y-axis. Then you can calibrate for F by comparing it to the stellar velocity dispersion, which we know correlates with the supermassive black hole mass from very local measurements. And indeed, this virial product does seem to scale with the stellar velocity dispersion. And so you can get an estimate of sort of the average F, the virial factor. Now, what's been shown as well, though, is that the broadline region size, so C times your time lag, also scales with your luminosity. And so this is really nice because now you can just measure a broadline region size. You have a luminosity, measure your full width half max, or measure, you use just a single spectrum to then calculate your supermassive black hole mass. And so then this has allowed supermassive black hole mass measurements even out to high redshift, because as you go to higher redshift, you have other broad lines like magnesium-2, carbon-4, and you can just use this sort of single epoch method to get an estimate of the black hole mass. Now, the problem is that these relations have only been measured on several tens of AGN and all in the local universe. They reside on the assumption that broadline regions are largely rotating. And so there's questions of, is there a substantial outflow or inflow component? There seems to be a significant scatter in the radius luminosity relation that could potentially be a function of the Eddington ratio shown here on the right. So this is a measure of the Eddington ratio. So as you go to higher Eddington ratio, so towards super Eddington, you go off the radius luminosity relation. And then there's also questions of, can we connect the broadline region to sort of the inner torus obscuring structure? And so this is sort of our goals with gravity. But before going into sort of gravity as the instrument and the science we've been doing, I also want to do a short interferometry review, because at least for me, before coming here, it was all just sort of a black box. So the basic idea is that you have at least 2 telescopes observing the same source, and they're separated by a certain baseline length. And so when you combine the 2 beams from the telescope, they're going to interfere with each other and produce what are called fringes. And so what the observations are providing us are the so-called complex visibilities as a function of the baseline length and the position angle, the projected position angle on the sky. So if you have a whole array of telescopes. So this V is has 2 components, the sort of visibility amplitude and also a phase, sort of your standard sinusoidal function. Now, what we know is that what you're essentially doing is you're taking the Fourier transform of your source in the sky. And you can relate the visibility amplitude as tracing the sort of size of your source, and the visibility phase as an offset relative to whatever your phase reference is. And then there's a third sort of quantity that we work with called closure phase, which if you have at least 3 telescopes is the sum of 2 minus another. And these are useful because this gets rid of, cancels out all the introduced phases due to the atmosphere. And so if you aren't doing phase referencing interferometry, you can work with closure phases and know that at least that's intrinsic to the source. And what closure phases are tracing is sort of asymmetry in your system. Okay, now with the 2 telescope interferometer, what you see here is the plane wave light source coming to your telescopes. And because they're separated by sort of baseline, the light in one telescope is going to hit it before it does the other one. And so essentially what you need are delay lines to correct for this what's called the optical path difference. And so, okay, you see this setup and maybe you think that doesn't look too hard. And so why has it taken it now to get something, a usable near-infrared interferometer to do AGN science? I mean, Michelson interferometers like these have been built over 100 years ago and used in stellar observations, while only now gravity has really started. And then you can think in the radio, we've also had for a long time huge arrays of telescopes, up to 40, as well as spanning the entire Earth with the EHT. And so really what is going on with optical and the near infrared? And it really has to come down to 5 different components that scale with the difficulty of doing interferometry. So first is what wavelength you're working in. So radio, you're at really long wavelengths, while in the optical and near infrared, you're at very short wavelengths. And so that's a factor of 10 to the 4, makes it 10 to the 4 harder. But really the big thing is the atmosphere. So as we know, the atmosphere is very turbulent. And before I showed you very straight plane waves coming into the telescope, but what the atmosphere is doing is it's really corrupting your wavefront. And it's introducing extra phase information. And so if you want to coherently combine the telescope light, you have to be able to observe at roughly what's called the coherence time of the atmosphere. And in the radio, this is minutes long, which is not difficult. While in the optical and the near infrared, it can be 10 milliseconds all the way down to 1 millisecond. And so you get another 10 to the 5 factor, making it hard. And here in the animation, here's what's happening. It's moving your fringes around such that you're not coherently combining the light. Now, the throughput as well, in the radio, it's something like 100% with antennas, whereas in the optical and near infrared, after you go through the whole optical train, you get something like 1%. Now, the collecting area as well, like I said, radio arrays, up to 40 telescopes with ALMA, so you have huge collecting area, whereas right now the best in the optical and IR is VLTI with 4 telescopes. And so that's another factor of 100. Now, where we do gain is in the photon flux, where there's many more photons in the optical and IR, so that helps us a little bit. But all in all, when you combine it, it is 10 to the 5 times harder, roughly, order of magnitude, to do interferometry in the optical and IR. And that's why it's taken so long to get to really realize gravity. And what gravity is really good at is what's called phase reference interferometry. So like I said, we need to correct with delay lines the optical path difference between paired telescopes. And so to do that, you observe both a phase reference as well as your science object. And so in the near infrared, we have to be able to detect our phase reference in observations as short as 1 to 3 milliseconds. And so then this is our biggest constraint. This limits how bright we can actually, or how faint we can actually go with interferometers. Now, while we're observing very fast on the phase reference, we move the delay lines, and we're correcting the phase, and then while we're integrating on the science object, it's called fringe tracking. Now, if your science object is bright enough, you can have your phase reference just be your science object. And this actually I'll show is the case with the AGN. Okay, so now I have a little movie that I think, because I'm part of the Gravity collaboration, I'm contractually obliged to show. But it's a really nice movie showing exactly what is going on within gravity. So first, we'll start with light coming from our source, traveling to Earth, down to Paranal. Here are the 4 UT telescopes. So we're just going to enter one telescope, bounce around on a bunch of mirrors down to the Coude focus. Okay, and our first stop will be will be here. And so those who can recognize this, this is the one away front sensor. And so really important with gravity is the adaptive optics system. And we have two, one called Chow in the near infrared, one called Macau that works in the visible. And the reason this is important is because we need to really get down to as close as we can to the diffraction limit so that we can inject as much light as we can into the fibers that feed gravity. Okay. Now let's leave the adaptive optics system. We'll back out a little bit. So this is going to control a deformable mirror, which is going to get down to the diffraction limit. And so now this is going to show that that's all happening in all 4 UTs. And then we stop here, and right around here is where the delay lines that are controlling the optical path difference between all of the different telescopes. And so then we enter the VLTI lab where gravity, there is gravity, sits. And so then our 4 adaptive optics corrected beams then are reflected into gravity. Lots of reflections, there's lots of mirrors. Okay, this first split is into the, so we do a split in H band. And this is just an image of our acquisition camera where we're making sure everything is aligned correctly. And so now let's back out. Now we're in K band. Now we're injected into a single mode fibers. Which are then fed into what's called the integrated optics beam combiner. So this is where all the magic happens and where the beams are split and then combined together to produce our interferometric fringes. Now finally, we go through a spectrometer to split the light, and then it's imaged onto our detector, which we can then use to make all of our measurements. Yeah. Okay, so this is just an overview of the whole gravity system and just to show how complex and how many different subsystems have to go correct to make gravity work. So as an overview, we're combining all 4 UTs for 6 baselines with a longest baseline of 130 meters. And what gravity has really done is vastly improve the sensitivity in terms of especially fringe tracking. And so we can go down to K of 10 magnitudes right now in fringe tracking. One limiting factor though is that there's only a 2 arcsecond maximum distance between our science object and phase of reference. And so that means, at least for extragalactic objects, we have to use the actual object as also the phase reference. And so really we can only go down to K of 10. Now, what does this mean? We have 3 milliarcsecond imaging resolution, and the stability and all of the systems within gravity allows us to get 10 microarcsecond astrometric accuracy. So this is sort of like us being able to image a car on the moon and have the accuracy of the size of a euro coin, or which is roughly the size of like a quarter on the moon as well. Okay, so before going into the AGN, and just want to highlight some of the other key science results. So of course, The main reason this instrument was built was to measure GR effects around Sagittarius A star. So our group has been monitoring stars orbiting the black hole in the center of the Milky Way. Here's the brightest one, S2, and here's its orbit after our gravity observations in 2018. And so these black points are the previous observations. You see lots of scatter and sort of big error bars. But then the blue points are our gravity measurements, and as we passed pericenter. And so two effects that we measured. One is the gravitational redshift of S2 itself. So as it went through pericenter close to the supermassive black hole, we saw that the light was redshifted, and that's sort of this peak here. Now, last year, we also were able to see the Schwarzschild precession of the orbit of S2. And that's where you sort of have a small shift in the orbit. And so with these, we've been able to put very precise measurements on the black hole at the center of the Milky Way, our distance to the center, and then measuring with high precision and high significance both the gravitational redshift and the Schwarzschild precession. And of course, back in October 2020, our director of our group, Reinhard Genzel, received the Nobel Prize for his work on proving or discovering the supermassive black hole at the center of our galaxy. Now, also, gravity can directly observe exoplanets. So here's just a sort of collection of recent results where we've been able to detect beta pic B, as well as get a high quality spectrum where we see the CO bands. Also HR 8799 get very high precision astrometry to measure the orbit. And so these are all papers that have been recently published. Okay, I know I'm running a little bit long, so I want to get to the AGN science. And so this is through the Gravity AGN project, where we're doing simultaneous broadline region and hot dust science. And it's an ongoing large program that we still have one semester left, where we're observing 10 type 1 AGN. And as I mentioned before, we have to use the AGN as both our phase reference and our science target. But what this does allow us is that within the sort of science channel where we have medium resolution spectra, we can do broadline region kinematics, size, and structure. And then in the sort of phase reference channel, which is very low resolution, we'll do hot dust size and structure. So first to the hot dust. And what we're starting with is we're looking at just the sort of visibility amplitudes. We viz squared, so it's just the square of the visibility amplitude. This work was led by Jason Dexter, who's a professor now at Colorado. And so in this paper early last year, we published 8 of our AGN observed with gravity. And what we do is we model the visibility squared as Gaussians because all of our sources are sort of partially resolved. And so the best we can do with most of them is to just derive the size. And what we find are sizes of about 0.3 to 0.8 milliarc seconds as expected, so 0.03 to 1 parsec. Now we can place our objects on the sort of hot dust radius luminosity relation. And what we've been able to do with gravity, at least with this sample, is double the sample of interferometrically measured hot dust sizes. And we find, as before, that the interferometric sizes are larger compared to reverberation mapping. And that's shown here on the right. There's a slight hint or evidence that there might be a luminosity dependence, which could suggest that there's a change in the radial dust distribution with increasing luminosity. So we see that the sizes increase significantly when you go to lower luminosity. Now, for the most nearby objects and the brightest objects, we can then try and reconstruct images from this data. And so for this, we need phase information. There's multiple algorithms out there to convert interferometric observables into an image. And so we've done this for 2 of our objects, NGC 1068 and NGC 3783. And so these are the first images of hot dust around AGN. And what's key here and why we picked these 2 is because they both show these non-zero closure phases, which indicates strong asymmetry and structure within the hot dust. So first, NGC 1068. This work was led by Oliver Fool, who is a postdoc here and who's now at ESO. What we find with the image is that there's a complex ring structure with a radius of about 0.24 parsecs, which matches the sublimation radius. However, it's quite thin with a height over radius ratio of less than 0.14. The near side is brighter. And if we zoom in and we plot also the maser disk information from radio observations, we find that our ring, the near side of our ring, is co-spatial with the maser emitting clouds. And so what this all points to is a very hot, thin disk of gas and dust near the sublimation radius. However, we do need to invoke a sort of thick molecular gas sort of outside of this radius to produce the observed visual extinction towards the AGN. But this is sort of consistent with the picture I showed in the introduction, where this is not your classical geometrically thick dusty torus. At least in the inner radius, we see very thin disk structure. Now with NGC 3783, which is work that I led, we don't have as good of resolution in the center, but what's nice is that we see both a primary central source, which has a size that matches the sublimation radius, and an interesting secondary offset source. The secondary offset source contains about 5% of the flux, and so you can ask, well, could this be a binary supermassive black hole? It's possible, but this would, based on the near-infrared flux, we expect black hole mass about 10 to 100 times less, orbiting at around 900 kilometers a second. And there's lots of gas and dust around to emit in the near infrared, there should also probably be a broadline region, which we don't see in the line profile. More plausible, what we're starting to do is spatially resolve the sort of or the gas cloud structure around the AGN. And here we can estimate that this offset source needs about 0.7 solar masses of gas at around 700 K to produce a K-band flux, which seems plausible for how close we are to the central AGN. Okay, so those are sort of primary results on the hot dust structure that we've been doing with gravity. Now, what's really exciting and what we like to do with gravity is to probe the broadline region. And so with gravity, we've been able to resolve for the very first time the broadline region, and we use a technique that's called spectroastrometry. So if you remember, gravity only has this imaging resolution of 3 milliarcseconds, which is much larger than the broadline region. So how the heck are we able to look at the broadline region? And so the key, here we go. The key is what's called spectroastrometry. And so we're using not the absolute phase, but the differential phase. So we're measuring the phase, interferometric phase, against the background continuum. And so if you imagine that the broadline region is in a disk, then clouds on a blue shifted side and clouds on red shifted side should show offsets from the central continuum. And it should produce this sort of S-shaped structure here. And then all of the differential phase also has a dependence on the line strength. But the key here is that there's this S-shaped structure in the differential phase that we should see. And so our first observation was 3C273, it was published back in 2018. And indeed, that's the case of what we see for 3C273 in the Paschen alpha line. That as a function of velocity or as a function of wavelength, we get this very nice S-shaped differential phase signal. Now, as a function of wavelength, we can also calculate the photocenter offset and map it on the sky. And indeed, we see the sort of straight line we would expect where we're tracing the kinematic axis of a rotating disk. And so under the assumption that that all the broadline region is a bunch of gas clouds under the gravitational influence of the supermassive black hole, we can do some intensive modeling, same as what's been done with reverberation mapping, and get an independent measure of the supermassive black hole mass and the broadline region structure. And here we're measuring a size of 46 micro arcseconds on sky, and a black hole mass of about, this is about 3 × 10⁸ solar masses, which is consistent with what's found with reverberation mapping, although we do find a slightly smaller radius than reverberation mapping. So this was the very first object we did. We published in Nature back in 2018. Now, since then, we've done 2 more. So this is IRAS 09149. And the really interesting thing that happened with this one is that we saw that actually there's a systematic offset between the continuum and the broadline region in this source. And so the signal for that is a very strong peak that follows the line profile. But still, you can see that there's a velocity gradient in the residual photocenters. And so we can still fit a broadline region model to this source and find a broadline region radius about 65 micro arc seconds and 10⁸ solar mass black hole. And so the picture here, what's happening is that in the background continuum is very asymmetric. So the continuum photocenter is different than the absolute photocenter of the broadline region, which produces a systematic shift. And then finally, 3783, we do the same thing. We see the S-shaped signal fitted with the broadline region model and find a broadline region radius about 71 micro arc seconds and a little less than, or about 3 × 10⁷ solar mass black hole. Now, what we can start to do with all these objects is place them on the radius luminosity relation. So this is also from my paper with 3783. And what we're finding, at least with 3, we have very small numbers right now, is that there is a broad consistency with our sizes, as well as our black hole masses, as what's been seen with reverberation mapping. And so then these 3 pictures are sort of our best fit models in terms of plotting the clouds on sky. In the next year, after our program's finished, of course, we'll have more objects that we're excited to publish. Now, you may think, could we combine both gravity and reverberation mapping data? And the answer is exactly yes. We can use the same broadline region model to fit both data sets. And what's interesting here now is that the reverberation mapping data is giving you the physical size, while the gravity interferometric data is giving you the angular size on sky. And so now, instead of having to fix your distance to your source, you can actually fit for a distance to the AGN. And so this was done back in last year for our first object, 3C273, not by our group, by another group. And so very nicely, they show the fit to the reverberation mapping data, the continuum, and the broadline region flux, and then as well as the gravity data. And then find a okay measurement of the angular diameter distance, about 500 megaparsecs. Now, of course, you're getting distances. You can then start calculating Hubble constants. And so for this one, they calculate something like 71.5 plus or minus 10. So the uncertainty is quite large for a single object. Now, what Shangguan, another postdoc here, has been doing, and we've just submitted this paper and actually just got the referee report back this week, doing the same thing for 3783. And here we're using reverberation mapping data from Misty's paper from last year. She has been nice to collaborate with us on this. And so here's our fit to the continuum, and then the broadline, the H beta broad flux, and then as well as our gravity data. And so we get also an angular diameter distance of about 40 megaparsecs. We can compare, for this one, for sure, we can compare with multiple measurements of the distance with Tully-Fisher relation. That's the Robinson 2021, and then of course the Tully-Fisher paper, the Cosmic Flows website, what's given on NED. This is from its membership within a group. And then of course calculating a Hubble constant, we get something like 65 with about 30% uncertainty. But what's nice is that this is showing that this method is consistent with the other measurements within the 13% RMS, and it shows the potential that if we could do this for a large sample, as well as understand very important systematics, we could maybe push towards a competitive and independent measurement of the Hubble constant, maybe even get down to 2%, but that is way far in the future. Okay, so that's sort of an overview of recent and results with gravity. Now I want to spend my remaining minute looking to the future, and that is Gravity Plus. And so Gravity Plus is an upgrade to Gravity that is actually under phase A review right now. And what's going to happen with Gravity Plus is several things. One, we're going to put laser guide stars on every single UT to vastly improve the AO, as well as vastly improving the AO system on each of the UTs to give us much better injection of flux into the instrument. Two, we're going to better control the vibrations, which is sort of our limiting factor right now in terms of the noise on our phase measurements. We've already made a GRISM upgrade to improve the throughput in the spectrometer by a factor of 2, and then also upgrade the VLTI to allow for wide field off-axis fringe tracking. So instead of that 2 arc-second limit, we can do up to 30 arc-seconds, and this vastly improves our sky coverage. So what does this mean for sort of extragalactic and AGN science? Well, here is a plot of sort of objects that are available to gravity, or AGN that are available to gravity. And this gray curve is sort of the current gravity sensitivity. Here's our fringe tracking limit of brighter than 10, and you see it's something order 10 objects. Now, Gravity Plus, we're going to push all the way to fringe tracking limit of 13. Now we can also do off-axis fringe tracking, so we're not limited really by this, as long as we can find nearby phase reference. Our sensitivity is going to be improved by something like a factor of 100, and so this opens up basically the whole population of quasars that we know of. And so what's nice is that if you remember, the differential phase goes as a function of the line strength, as well as the size of the broadline region. And so as you go to higher redshift, you get stronger broad emission lines redshifted into your K-band, which then increases differential phase signal. And so even though they're getting fainter, what we really care about is the line to continuum ratio. So some things we could do with this. Number one, we could trace supermassive black hole galaxy coevolution. Namely, we can measure black hole masses out to at least redshift 3 and look at the scaling relations between black hole mass and bulge mass and black hole mass, stellar mass as a function of redshift. There's some contradicting observations right now using the single epoch method, but Gravity Plus will substantially increase the number of black hole masses as well as the quality of supermassive black hole masses to get better estimates of the scaling relations as a function of redshift. Secondly, as you might have in your mind, we can potentially detect and resolve supermassive black hole binaries, sub-parsec binaries. Two different ways we can think about. Number one, look at the hot dust around them. They should have a hot dust size much larger than what you would expect for the sublimation radius of a single AGN. Also, if they both have broadline regions, there would be a very clear differential phase signal. Of course, we're limited here by actual candidates to go look at. We can't just blindly pick AGN, but if we have good candidates, we can go and test and really determine whether they actually are binaries. Okay, so I've gone a little bit over time, apologies, but here I am, my summary. Number one, gravity has really opened the door for high spatial resolution studies of the sub-parsec region around the AGN. We've been producing the first images of hot dust around AGN, revealing interesting substructure, as well as spatially resolving for the first time the broadline region around several AGN and testing the local scaling relations that are used at high redshift. And then Gravity Plus has then the potential to completely blow it wide open, do things like supermassive black hole galaxy coevolution, look at black hole binaries. I haven't mentioned tidal disruption events. We can go all the way out to Z of 6 if we can find proper targets. And there's many more things you could do with Gravity Plus. Okay, thank you.
Thank you so much, Taro. So I'll do the clapping. Yeah, so I wanted to say that we're going to stay extra time for those of you who want to continue staying longer to continue the discussion. But let's start with some questions. So this is really meant to be informal, and so just raise your hand when you have questions.
So, can I ask a question?
Sure.
Hi, Taro.
Hi.
So, so do you intend to detect any inflows and outflows in the sub-parsec scale structures? Because the BLR regions are very hot gas with multi-phase components, multi-ionized components. So, do you expect to detect anything like across or along the line of sight?
Yeah, so that's something we definitely want to look into. We haven't detected, well, okay, one of our objects, IRAS 09149, we can actually fit it with both a completely rotating disk, as well as an outflow component. Thankfully, it doesn't change the black hole mass. Otherwise, we haven't really been able to detect any inflow or outflow. One thing that we are working also on is combining gravity and reverberation mapping and do it in a velocity resolved way. And here we would expect to better be able to detect inflow and outflow components. In principle, we should, yes. I think the sensitivity and our uncertainties right now aren't good enough right now.
Absolutely. And what are the choice? I mean, why are these sources chosen? Like, what are the criteria for the choice of these sources?
One, I mean, the main thing is they're bright enough. So that our limit is they have to be brighter than K of 10. And so that really limits you. Yeah, that's the main limitation. And then also being in the south to be visible with gravity.
Great. Any other questions? So I'll ask a question. First of all, fantastic talk, Taro. That's really impressive what you've been able to do with gravity. Oh, I see Anil is. So I'll quickly ask my question and then I'll let Anil go. So I guess I had just some sort of fundamental questions on the limitations with this technique. You said with the upgrades, you can go to 14th magnitude and 30 arc seconds for your off-axis fringe tracking. How much does that improve sky coverage? And I was just wondering with, for example, looking for supermassive black hole binaries, you know, how many targets can you access with this upgrade?
So we did an estimate on for the phase A review, and we started with the million quasar catalog. And given the limits in terms of off-axis fringe tracking and nearby stars, we can get up to several thousand AGN quasars all across all of the redshifts. Yeah. Of course, the sky coverage is obviously best in the galactic plane, but that's where we don't have any AGN, unfortunately, right now. I don't remember the actual number in terms of sky coverage.
Okay. Great. So I don't want to take up time. So Anil?
Yeah, this is kind of maybe a little bit more specific, but I kind of wanted to ask about the result with the dust sublimation radius or the dust radius. where you're showing that it seems like it kind of is deviating at lower luminosities. I was just curious if you have ideas on the physical mechanisms for what might be going on there.
A possibility would be that this could be an indication of a feedback, and the AGN sort of blowing out and decreasing the covering factor of the dust around it. And so at oh wait, that's the wrong way, I think.
Well, like the covering factor would be smaller at larger luminosities because there's more, like essentially you'd expect maybe a ring rather than a shell or something like that. Is that kind of?
Yeah.
Okay, thanks.
Anka?
Hi, thank you, Taro, for such a nice presentation and definitely a great summary of what's going on with the AGN physics and the latest results. And I was pleasantly surprised that we get some new independent measurements of distance with this new technique. And I was just curious because I'm involved with the MCP collaboration, the Mega Maser Cosmology Project. I was just curious because I know they're working tirelessly with VLBI data to find, cosmologically, so independent distances from all the other methods. And it's pretty much the same objects that you have been doing these measurements as well. So I was just curious, like, is this method more efficient? How do these results compare with the results from the Mega Maser VLBI measurements and modeling that goes into converting the distances into new constraints for the Hubble constant? Can you maybe comment a little bit on that?
Yeah, I'd say I don't think it's more efficient because of the fact, I mean, the reverberation mapping component really makes it, you need to build up your light curves to do the reverberation mapping part. So I would say it's probably not more efficient than Mega Maser and what you're doing with the Mega Maser Cosmology Project. And then also there's a lot more modeling going into, I mean, with the Mega Maser, as I understand, you're essentially fitting Keplerian disk. Here, there's a lot of different, I mean, you were using somewhat of a simplified model, but there's still a lot of systematic errors I think we still need to understand to really make this a viable way to get a competitive Hubble constant. So I'd say Mega Maser is probably light years ahead of what we can do here. This is really the first time we've attempted this. One issue that we've been thinking about, and we know it might be a problem, is the fact that at least right now, reverberation mapping, with reverberation mapping, we're doing one line, H beta, but then with gravity, we're in a different line, bracket gamma most of the time. Well, 3C273 is Paschen alpha. So we do need to understand whether there's systematic differences in the broadline region structure as probed by the different lines as well. And so really we don't want to claim that we can, anytime in the near future, get anything competitive in terms of the Hubble constant, but it's a nice independent way to also get distances.
If I may, I think you should be a lot more optimistic about this, just coming up with this new method and obviously testing it and sorting out the systematics. With the Mega Maser method, it's kind of like a bottleneck in there's a problem that we're not able to find more Mega Maser disks out there in the universe. But if with Gravity Plus, you're gonna be able to do this for, I don't know, thousands of AGN, then you're definitely not light years away from the Mega Maser Cosmology Project. So I think it's a fantastic idea, and I'm definitely looking forward to seeing some great results. I wouldn't see it in competition. I don't know. It's sure, but I think it's great. I think yeah, you should definitely be a lot more optimistic about what's coming out of this. Thank you.
Great. Archana?
Thank you. I just had a question. You mentioned it's currently magnitude limited, but I was wondering if it would be possible maybe in the future to use gravity to detect maybe masses in the intermediate mass black hole range.
That's a good question. Yes. One way to try and get intermediate mass black holes is to go to the nearest or to the best candidates right now that we have, I think in globular clusters, and try and do stellar astrometry, follow stellar orbits in the very central regions with gravity plus. And so that is one emphasis we put in the phase A science case is, yeah.
Great. Any other questions? Oh, there are a lot of hands going up here. So, Jeffrey.
Hi, Taro. Thanks for the talk. That was great. I was wondering if you could go back to the slides where you had the, I think it was the broad line regions mapped and the different colored dots.
Let's see. This one?
Yeah. So on the one on the bottom, NGC 3783. So if I'm understanding that correctly, it's like, this is showing like half the material, like on the bottom right, is like coming at us and the other part's going away. Could you maybe speak on that a little more? I'm trying to find like, it looks in the other ones, there's kind of that case too, where I kind of feel like half of red is on one side and half is on and half of the other half is blue, but I'm not really sure. What does this necessarily say? I guess inclination angle also plays a part of it, right?
Yeah, so this is showing the sort of velocity structure of the disk. So, so let's see, it's telling you the direction of rotation. I just have to remember which way 3783 is inclined. So it must be going this way. So these clouds are coming sort of towards us in the line of sight, and these are going away from us as they're rotating around the black hole. Yeah.
Okay, great. And I also had another question. I guess the sources that you choose from also, I guess, always have to be type 1 sources.
Yeah,
that's correct. Yeah. Okay.
Yeah.
Thank you.
I mean, with the problem with type 2, so we were able to do 1068, but that's because it's like the brightest type 2 AGN. Gravity has problems, I think, right now with the very red sources. So obviously type 2s. With gravity plus, that should improve. And so there's prospects for extending sort of our imaging campaign to do more type 2 AGN.
Okay. Maybe it would be interesting to look at maybe a changing look AGN, if you could, I don't know. Yeah, thanks.
Great, Jeffrey. Ryan?
Hey, Taro, great talk. Thank you so much. I had a question about the binary systems. Not a ton of targets, and so I'm wondering what are the sort of the constraints as far as how local would these systems have to be in order to be able to resolve these systems and actually be able to measure the size accurately and be able to say for sure that that perhaps the sublimation radius is too large to be a single source.
Yeah, so first, yes, there's not a lot of targets, although with all the various surveys that should be coming online in the near future, we should start getting a lot more candidates, at least, that we could start looking at and targeting. One way would be, so if the left is true, then there's a sort of a cavity, and so we should see a decrease in the K-band flux as a function, or as a ratio of the optical flux. And so maybe one way to go after these would be to look at the ones who show a strong deficit in near infrared emission. In terms of how far out, at least for the K-band or for the hot dust measurements, well, you can't go too far up in redshift because then you're redshifting out of the K-band. So I think the prospect is out to something like redshift 1 or so. We can reliably start to resolve the binaries.
Thank you.
Great. Gabby?
Hi, Taro. This is a really great talk. And so it's more a comment than a question. I think it's a really nice overview of gravity, and it's very exciting for me to see, compared to what we were doing a decade ago. This is like, wow, it's like the difference between a phone landline, with a dial and a cell phone, so very nice work. I wanted to say, I could see your frustration at having to show the movie, but just the movie for gravity, it eats up on your talk like a whole chunk of minutes. But just as an encouragement, I was really happy that you showed it for the sake of my students, because it really shows why you get 1% throughput. It really shows how it's just the complexity of the system, and I love that there was a little sound on every reflecting surface. You should make the audience count them.
Well, thank you.
So very nice job.
Thank you.
Yeah, I completely agree. I should say that, if it's okay, Taro, to just continue some of the discussion, that would be great. But feel free to tell me that you're hungry and you want to go have dinner. So I'm aware of the time difference.
I'm happy to.
But it would be fun to chat informally for anyone who wants to stay on.
Can I take down my slides because I haven't been able to see anybody?
Sure. I know how that feels. Yeah, staring into the void. We've all, become zombies.
There we go. Okay, good.
Great. So I wanted to, if no one's, any other people want to ask questions? I want to ask some sort of naive questions because I'm still trying to wrap my head around this amazing instrument and what are the fundamental limitations. And I guess I was just wondering, because you had a very nice slide in the beginning showing, interferometry across the wavelength regime and starting with radio all the way to near infrared optical, and you were talking about the coherence time and the limitations. And I guess I wanted to understand, like, fundamentally, is there a way to push this to shorter wavelengths, like the optical, where you can really maximize the spatial resolution and minimize the sky background?
I mean, what gravity was able to do was take advantage of new detectors, which had very, very low readout noise. And so we can do very fast observations and track the fringes. Yeah, optical, I think, is really tough. I mean, of course, there's optical interferometers like Chara, but the limitation there is that you can only do very, very bright things because you have to at least detect things on very short time scales. And so really there has to be a big technological breakthrough in terms of probably detector science, I think.
Great. Any other questions? There are all these experts on AO observations and reverberation mapping, although I think Misty left. Any other questions, comments, exciting things that people want to do?
Coming from someone with zero observational experience, and I just know about this from just hearing about it essentially, does gravity use any adaptive optics, and would that help with the optical range at all? Like, I know you said the atmosphere has a lot of interference, and that's a lot of the reason why the optical isn't so good, or it's really hard in the optical.
So yes, gravity depends heavily on adaptive optics. We have to have an adaptive optics system, and so really the gravity plus the big upgrade is the adaptive optics system there that will improve our fringe tracking limit. In terms of the optical, maybe I would have to think about it. The problem is adaptive optics systems, at least current ones, you're still not correcting for what's called the piston mode, the average wavefront difference between the two telescopes, and then in the optical, you're at even shorter coherence times, and so you still need to be able to fringe track very, very fast if you want to push to the optical. But I would have to think about it.
Great. I mean, it does such great things. So, you know, it's sounding kind of greedy, like trying to push it even more to the shorter wavelengths where the diffraction limit gives you the best spatial resolution. But yeah, amazing stuff. Is there any kind of synergy that you've been thinking about with VLT gravity and say JWST, for example?
Yes, I think there could be. I mean, for 3783, I made use of symphony data to connect what we're seeing in the broadline region, the sort of geometry and orientation with the hot dust, and then extending out to the sort of circumnuclear ISM. And so that was very useful. So I could see also getting JWST, similar JWST observations would help to sort of put it all together in a coherent and comprehensive way, connecting all the different scales as you go all the way down to sort of accretion to scales.
Yeah, I think that would be exciting because actually I was looking at your symphony data, which is amazing also. And there are some unusual things like in terms of the spatial distribution of, say, the coronal line emission. And I was kind of surprised seeing bright off nuclear emission in certain lines. So it'd be interesting to understand the origin of that.
And that was one thing I didn't have a chance to mention in my talk, is that with 3783, with gravity, we were also able to measure the size of the calcium-8 emitting region, at least the nuclear one. And so that's a difficult measurement because, well, especially calcium-8 is very faint. But then gravity plus, we could probably try and push to do more, especially if we can go after silicon 6. The silicon 6 line, which is much, much brighter than calcium-8. And then use the gravity measurement, pull out near-infrared IFU measurements to sort of connect the gas as it's going all the way down.
That would be exciting. Yeah, I'm curious to hear your next results.
I'm sorry, I missed that. Did you say you are going to do that, or you've done it already?
No, it's a possibility we could do that. Not till gravity plus though. I did it for 3783 with calcium-8. And we've thought about going after some silicon 6 targets with gravity, but the sensitivity is not good enough right now.
No.
And what was the size of the calcium-8?
4 milliarc seconds. So what did that translate to? I can't remember in terms of physical size what that translated to. Several parsecs, I think.
Okay, wow, that's interesting. Any other questions? If not, we can thank Taro again for a fantastic talk. And so I'll do the clapping. So thank you so much, and we can let you go have dinner. And peace.
All right, thank you. Thank you very much